So yeah, I would like to present some work I have been doing with my supervisor for the first months of my PhD. So I will go directly to the first slide. In this slide I want to show you the kind of problem we are interested in, and then the rest of the talk I will show you the progress we have made so far. So we assume that there's some physical system or some quantity of interest that evolves in time, and the evolution is successfully modeled by this map psi. So by this I mean that provided that we know the value of v at time j, this map tells us exactly and without errors the value of the quantity at time j plus 1. The problem is that the initial condition of this recurrence is only known with some uncertainty. So we only know the probability distribution of the initial condition. And the uncertainty in the initial condition will be propagated by the map psi. So this will form a sequence of random variables that I call the signal process. So in particular, if the map psi shows some chaotic behavior or unstable behavior, this will lead to increased uncertainty of the value of the signal as time evolves. Fortunately, it is often the case in the real world that we can observe the evolution of the system as time evolves. So in this talk, I will assume that at each time we can observe the signal, and the observations are of this form. So you should think here of the observations as a very low dimensional projection of the signal, which is perturbed by some noise. And of the noise, we will only assume that each of these W's are centered and have finite variance, so no causality assumed. And I want to emphasize again that this projection operator reduces very much the dimension of the original signal, to the point that I will show you an example where the signal is infinite dimensional, but the observation is only of a finite amount of modes.
The P can be a nonlinear operator? Or
Linear.
Linear.
Yeah. So the goal of the talk is to show you some conditions on the map psi and the observation operator P, under which the signal process can be tracked in the long time regime. So this is not a very mathematical statement, so I will try to be more precise in the next slide. So as we have seen this model, the main object in this kind of research area is this probability distribution of the signal process given all previous observations. And as Robert pointed out, it is not possible to compute analytically these probability distributions. It's out of the question. So people have tried to come up with approximations to these probabilities, like particle filters. Tomorrow we will see a Sample-Kalman filter and so on. But one of the main messages of the talk is that we believe that in order to build better approximations, it is desirable to understand as much as possible the properties of this probability distribution. And that's what I'm going to try to do today. So the mean with respect to these probability distributions is called the optimal filter and will be denoted Vj hat, and it's optimal in L2 cells just because of the optimality property of conditional expectations. And the result that I will show you is of this type here. So I will try to explain what this result tells us about the filtering distributions.
I want to make sure I understand the notation. So Zj is any data that is any value of the system that is consistent with the data. That's what you mean by?
Yeah, so the optimality property of the optimal filter is that with the observations that we have at this time, the optimal filter is the best possible filter in the sense that if we construct any estimator set J with this information, it will be the optimal filter will be closer to the signal than this other estimator. It's a property of the conditional expectation, yeah.
What the expecting the expecting the second line is respect to what?
In the second line, yeah. So Vj and Z and Yj form a sequence, and that sequence has uncertainty by two things. Firstly, because of the uncertainty in the initial condition V0, and secondly, because of the uncertainty in the realizations of the observations Wj. So this expectation averages over both.
The mean is the minimum variance estimator.
Yeah, that's it.
Is what that says.
Yeah, but it's true that it is minimal if we assume that we are averaging over the measure with which the signal is initialized. Yeah.
Yes.
Do you typically know psi, or is that also you're trying to infer?
No, we assume that we have a perfect model.
You know what it is.
Yeah.
Can you just one final thing? I think I missed the definition of sigma. So that's
That's the
definition of the.
this is just a
That's a
sigma algebra, but you can think of this as the information at time j. Is everything okay? So yeah, the kind of result we want to show is this one. So this result tells us, first of all, that the optimal filter is close to the signal. The optimal filter, as I said, is the mean with respect to the filtering distributions. So we get that the mean of the filtering distribution is close to the signal. But we also get a result about the variance of the filtering distributions. So we get a result that tells us that we are more certain that the optimal filter will be around the signal. And remember here that epsilon is just the strength of the noise in the observations. Okay. So this tells us that we are close, and of course this result is most powerful when the noise in the observations is small. Okay. So the rest of the talk I will show you these conditions on P and Psi, under which we can show the red results in the previous slide. So in the first slide, in the first part, I will assume that I minus P is psi is globally contractive, and in the second part, which is my favorite part, I will just assume a local condition. So maybe at this point I can discuss a bit all the 3D bar algorithm. So the 3D bar algorithm is defined as follows. To estimate the signal at time j plus 1, we find a compromise between the model and the observations. So it's the arc-mill of this long. So this long, we want to make it, this part we want to make it small because we want to use the model, and then this part we want to make it small because we want the observation to be close to the 3D bar algorithm. So
The MJ here, the VJ from your slide before.
no, this is the 3D bar algorithm that I mentioned in this slide, and this is a suboptimal algorithm that I will use in order to get our result for the optimal filter.
I assume these norms have covariances attached to them.
Yeah, I want. Sorry, I wanted to. So this algorithm is a practical algorithm that has been widely used in weather forecasting, but in this talk, I'm going to use it as a way to show our results about the optimal filter. So these two longs here, this is how much you trust your model, and this is how much you trust your observations. So the more precise your observations are, the more weight you want to give to this part. So in particular here, I will put epsilon square because this is the strength of the noise. So the smaller the strength of the noise, the bigger you want, the most important you want to give to this part. So after some algebra, you can show that you can write the solution to this minimization problem as a convex convolution of the model and the data, where here S is an operator that I'm not going to write here, but involves the Kalman scale that we saw twice this morning. So for particular choices of S, I will for particular choices of S, this can be written as follows. Where P is the observation operator. And this parameter here is a parameter that represents the importance you give to the observations relative to the importance you give to the model. So for the rest of the talk, as I am particularly interested in the case where epsilon is small, that is when the observations are very informative, I will choose here eta equal to 0, okay? Which is the extreme case where you trust most the observations. Yeah, so what I want to take about this is that this is an algorithm that has been widely used in real applications, but in this talk we are going to use this algorithm with the choice eta equal to 0 to get bounds on the optimal filter.
S maps something to the dimension of after the projection?
Here in this talk we see the observations as living in the same space as the original signal. What is lower dimensional, but we see it just as a part of the whole signal space. So, for example, if the whole space is R3, for example, the observations may be the first coordinate, and then the second coordinate, we leave it as is. So yeah, the first part of the talk, I'm going to assume that I minus p psi is globally contractive, and I'm going to use this filter that I have shown you here, which is, as I said, a form of 3D bar algorithm to show this result. So the proof is in 2 steps. First, we show this result here, where here Mj is the 3D bar algorithm, and then by the optimal property of the optimal filter, we deduce the result for the optimal filter.
So, I mean, the same question as here. It seems that you assume that you observe the whole signal. Otherwise, I don't understand the notation either here nor there. You assume that the y's have the same dimensionality as the v's or the m's.
No, I don't assume that. So I assume that they are low dimensional, but they live in the same space. So if you see what I mean.
Yeah, I see what you mean, but then I mean, you seem that you're putting zeros in places where.
Yeah, it's just for mathematical convenience, because the proofs that I want to show you are more clean if I write them that way.
It should not be 0, by the way. It should be the bond equivalence, or I don't know exactly what it should be.
Sorry?
So the place where you do not observe, you should keep these elements in your y vector should be equal to the model estimate.
Yes.
Or something.
To
Not
zero,
0.
yeah.
Yeah, okay. Yeah, the signal. Okay, that's cool.
So for example, yj, you can think of it as this is what you have, and then you put zeros otherwise. So here you observe only two coordinates, and then the rest you put zeros.
So in this case, 3D var works as well.
Sorry?
So in this case, 3D var works as well.
Yeah. So the proof is very easy. So we write the 3D bar. Recall that yj plus 1 is given by this. So we write mj plus 1 like in this form, and then we have this identity for the signal process. So if we subtract, we get rid of this term here, and then we take expectations all square here. So this term survives here, and then we subtract this, and then using the independence and and the fact that I minus p psi is globally contractive, we obtain this estimate. And now, by using global inequality, we get the lim sub result for the 3D bar, and then we get the lim sub result for the optimal filter by the optimality property. So as an application to this, I'll just, so that you get some intuition as to what's going on. This tells you that in the case where the map psi is linear. This condition that we had in the previous slide holds if and only if the spectral radius of this matrix is less than 1. So what this condition here tells you is that the parts of the dynamics that expand should be observed. So in an example here, if you have that the matrix L is of this form, with this block having a spectral radius bounded by 1 and this bigger or equal to 1, then, for example, for this observation operator, and perhaps here you can see what we meant by the observation being the same space as the signal. So for this choice, so only observing the parts that expand, you can get the lim sub result for the optimal filter. So you only need to observe the parts that do not contract. And this same intuition will hold for the second part of the talk. So the second part of the talk is more interesting for me. The map psi that we want to study here is the solution map to a differential equation of this form. And those are just usual assumptions that guarantee that the quadratic nonlinearity B is energy conserving, and that the dynamics are dissipative. So why do we want to study this kind of differential equations? Two main reasons. The first reason is that there are many models that can be written in that way, so we create a unified framework that works for all those problems. And these kind of equations have been widely used for testing filtering algorithms. The assumptions that we need are two. These are all the assumptions that we need for the theory that we are writing. These assumptions are not strictly needed for the theorem that I'm going to show you, because I'm going to show you a simplified version of the theorem. So the first assumption is an absorbing ball property, but we are only going to use here that this map psi is forward invariant, meaning that it maps an initial condition in this ball to this ball again. And the second property is a local equivalent to the global property that we had in the first part of the talk. So here, this coefficient alpha depends on this radius of the absorbing forward invariant ball. So the same result as before, but now this kind of 3D bar algorithm doesn't work for the proof. So we created another modified version of a 3D bar algorithm that allows for noises that are very general, as I said before. So what we do is, this thing in brackets is the 3D bar that I used in the proof of the first part of the talk. So, and this P is the projection operator into the absorbing ball. So what we do is, if this 3D bar algorithm lies outside the absorbing ball, we just project it into the absorbing ball. And if it already is in the absorbing ball, we leave it as it was. So now, for the talk, I'm going to use this simplified assumption that is not strictly needed, that the initial condition of the signal is in the absorbing ball. Because I think it's very easy to see the idea of the proof in this context. And then the steps of the proof are the same as before. We prove this result for this suboptimal filter, and then we conclude by the optimality property of the optimal filter. So the proof uses these 2 points. The first is that since the map psi is forward invariant, and we assume in this talk that mu0 is in the support of mu0 is in the absorbing ball, then all the silent sequence will be also in the absorbing ball. And the second is that by construction also the 3D bar algorithm is always in the absorbing ball, because if it's not, we project it. So the proof is the same as before. The only thing that changes is that we have this inequality here, which is a consequence of these 2 ballets here. And then the second change is that we can use that both Mj and Vj are in the absorbing ball to have this uniform bound here. So this allows for, I want to emphasize that this allows for very general noise in the observations, which is an improvement over theory that had been developed for the 3D bar algorithm.
Alpha to be strictly less than 1.
Yeah, it's between 0 and 1. So examples where the theory can be applied. I'm going to show you three examples. So this one we saw it in the morning in the first talk, and it was quite good that you showed the first coordinate of the Lorentz 63, because what we can show is that only observing that coordinate at discrete times and with some noise on top of that, we can accurately infer the positions of the other 2 coordinates that we don't observe. So here this operator P is just telling us that we observe only the first of these 3 coordinates. And the theory for that is based on this paper by Hoydel, also Lantiti, and another paper by Kodilo, Abhishek, Shukla, and Andrew. The second model that fits into our theory is the Lorentz 96. So I will just say that for this model we need to, for example, this operator is enough to guarantee that the optimal filter is close to the signal. So this tells you that we observe the first component, the second, the fourth, the fifth, and that is enough to infer the position of the third and the sixth and the ninth. And the proof of that will be hopefully soon available. Well, it's available, but for everyone. So,
Can I ask a question? Do you assuming that you observe every time step?
yeah, every j. So psi is the h time solution operator to that ODE that I showed, and we are observing each h time interval. So
I think the question might be getting at how frequently do you have to make the observation?
Yes, sorry.
oh, okay.
Because it's not discretized. So
No, I realize.
Yeah.
What about, yeah.
So in the proof of that of the results that tells you that we can apply this model to our theory, in the proof you can see, if you follow the steps of the proof, how small you have to take h for the theory to hold. Of course, there is a h that's, if it's too big, you can't say anything. And the third example is the Navier-Stokes in La Tulitor, so with periodic boundary conditions, so that we can write the solution in Fourier form, and this tells you that what we need to observe in order to track the signal is only the first modes of the solution. So this lambda here depends somehow on how predictable your solution is. So, for example, just so that you get an idea, this nu here is the viscosity in the Navier-Stokes equations. So the bigger the viscosity, somehow the more predictable the behavior of the system will be. So lambda here can be taken smaller if the viscosity is bigger. And the results that guarantee that our theory can be applied can be seen in those two papers. I have the references at the end. So basically, I wanted to convey two ideas. The first idea is that understanding the behavior of filtering distributions is important in order to build better approximations of it. And the second idea is that we can use some suboptimal filters like the 3D bar of this projected version of the 3D bar to get a better understanding of the filtering distributions. And it may be also the case that this projected version of the 3D bar algorithm that we constructed to show the result for the optimal filter is useful in practice, especially if we are trying to filter dynamics that have a dissipative behavior. So thank you for your attention.
Thank you. We have time for questions.
So I wonder, so for example, given these practical problems, how easy it is to find these suitable norms and also these small balls. I mean, how would one come up with these absorbing balls in practice?
No, I mean, the fact that these models satisfy the absorbing ball property has been well known for decades. The more subtle thing is to show which parts of the system you need to observe in order to the I minus p psi to be contractive. And that is what we have been doing for the Lorentz 96, Lorentz 63, and Navier-Stokes.
So you mean that the models that you have been looking at all have the smoothing properties so that they're
Yeah, so they have a dissipative structure that tells you that if your initial condition is in a bounded set, it will eventually be in the absorbing ball after a finite time. After a finite time.
Two questions, if I may. So the first one is following on my earlier question. So, for instance, for Lorentz 63, you have this h, this time interval. How does it compare to 1, which is sort of the typical physical time scale, if you like, of the Lorentz 63 model? How
yes.
does it change?
So the theory that we have, there's a gap between theory and practice, that's always the case in Silk. So the theory that we have works for small h, quite small h, like 10 to the minus 5 or so.
Oh, okay. Okay.
But we know by numerical experiments that it is reasonable to expect that things could be proved for larger h.
I would guess so. Much
I mean, the thing that cannot happen is that you can't prove things and you can't see that in experiments.
Another question. So you talk about modified 3D var. I didn't really get that. So what is the modified 3D var you were talking about?
Yeah, so the point is that since all these models satisfy this absorbing ball property, that tells you that the solution is in a ball after a finite time, then if your filter gives you a value, a very large value that lies way outside that ball, you know for sure that that value corresponds to an observation that has a very large noise.
Okay.
So then if you know that observation was not good, you don't want to take it. You want to have your filter in the ball because you know that the signal is there.
This is, I would say that this is assuming that you've defined your 3D var as, that you already assume that you have perfect dynamics in place. If this is what you assume to be 3D var inherently associated with 3D var, then I would agree. If you do not, if you allow for any psi to be present there, that does not necessarily have to be true. Do you see what I'm getting at? If you're considering 3D var with perfect dynamics, or if you define your 3D var to be a filter that uses perfect dynamics, I agree. If you allow for errors in the dynamics, then that doesn't have to be true. What you just said.
It's true. I mean,
I agree if you say that if 3D var uses perfect dynamics, then yeah.
But even if the dynamics are not perfect, but you know that the solution will be in a certain ball after a certain time.
You don't have to know it. Well, it depends whether you know anything enough about your true dynamics.
Well, yeah, but it might be reasonable to believe that you have dynamics such that you know that after a certain time that the value cannot be 100,000 something.
If you have noise, you have a probability associated with that. You don't know. You only get into the ball or a region with certain probabilities. You have to account for that too. But you,
But I had another question, which is I sort of jumped into it. It's related to the final part that you mentioned on Navier-Stokes, the third part. Do you have any estimates, for example, of even rough ones? How many modes should you take into account depending on?
There's a formula that tells you exactly. Well, that formula is well known. It's not something that we have shown. You can find it in the second paper there, for example.
Okay, but and the final
So there are several things that of which that lambda depends, but you can see it in the paper.
The final is not a kind of guilty mentioning this. Because you're assuming that you can observe the Fourier modes independently up to a certain Fourier mode, right? You see what I'm saying? I mean, there is an inherent assumption that you're able to observe Fourier modes independently up to a certain threshold. But if you can't do this, then there is a problem. And I feel guilty about this because I should have done something on this a long time ago. As some people in the audience might know. But do you see what I'm getting at?
Yeah.
You were sort of introducing you were thresholding in the Fourier domain.
Yeah.
If you somehow cannot separate Fourier modes independently, then you might have a problem.
Yeah, I guess that's the case.
Yeah.
okay? One question? Right. If not, let's do it again.